Like I said, we need to remember these definitions, and not just for this chapter, but this is something we're going to use throughout the rest of the year. And when we're talking about the ability to differentiate a function, that's basically asking the same question as, are we able to compute this limit? If this limit exists, then the function can be differentiated. If the limit does not exist, then the function cannot be differentiated. Okay? And the same thing with this one. If the limit exists on this one, then the limit's going to exist on this one. It works the same way because they're defining the same thing. It's just a slightly different way of approaching the idea of the derivative. All right, so if those limits exist at any particular point, then the function is differentiable at that point, which just means that we can take the derivative. If the limit does not exist, then the function is not differentiable at that point. Makes sense, doesn't it? All right, so when might that limit not exist? What types of things are we going to run into in the graphs of a function that are not going to allow us to differentiate? Any ideas? Asymptote. Okay, asymptotes would be one. Discontinuities would be another. Hit two of the main three there. So an asymptote or a discontinuity, and those actually end up being the same thing. Vertical tangent would be another one where you can't differentiate. And the reason is, what? You guys tell me. Why wouldn't we be able to differentiate where we have a vertical tangent? Okay, I think I heard it out there. I heard a lot of stuff. But a vertical tangent means that the slope of the line at that point is going to be infinite. Okay, we can't find the slope of a vertical line. It's undefined. So since the slope is going to be undefined there, that means that the derivative is going to be undefined there because the derivative is the slope, right? So when we get a vertical tangent, we're going to end up with an undefined or an undifferentiable function at that particular point. So an example of that, you guys know what the function, and this is not the example, but you know what the function y equals x to the third looks like? Okay, do you know what the inverse of y equals x to the third is? The cube root of x, or x to the 1/3, right? Well, that function looks like this. Since it's the inverse, it's just going to look like that. And what we end up with is a vertical tangent line right here. Okay? So at that point, the function y equals x to the 1/3 is not differentiable. It's differentiable at every point except for that point. Okay, so when we're talking about differentiability, usually we're talking about differentiability at a point, not necessarily for an entire function. There are some functions, and they're crazy, and we don't encounter them in regular everyday math. But there are some functions that are not differentiable at any point. And if you really want to think about that, it's kind of a deep thought. It's pretty crazy if we would have a function defined at every point, but not differentiable at any point. And I think there's an example in your book, one that Carl Weierstrass came up with a while ago, back when he was alive, that was kind of interesting. Anyway, we've got those two. Vertical tangent would not be differentiable. A point of discontinuity, including an asymptote, would not be differentiable. And then finally, a corner or a cusp. There's a slight definition variance between a corner and a cusp. A corner would be like something we would see in an absolute value function. And a cusp is a little bit more defined. A cusp would look like that, where basically what we have happening is we have a vertical tangent at the corner. So there's a slight difference there, but it's the same idea where we have a sharp corner there. Okay, so those three places we're not going to be able to differentiate a function. One thing you want to think about when we're thinking about differentiability is something called local linearity. If you want to determine if a function is differentiable, so if we're going to be able to figure out what the derivative is at a point, basically what you want to do is you want to look at a function in a very small viewing window, and if it looks like a line, then you can take the derivative. If it doesn't look like a line, if it still looks like a corner, as you zoom in on it, if it still looks like a corner, or if there's still a discontinuity there, then you're not going to be able to take the derivative. So local linearity is this idea that if we zoom in enough, any function is going to look like a line, or any differentiable function is. And it's actually really useful for us because then we can use lines to approximate curves. And that's something we're going to do later on. It's called linear approximations. Oops, that's not supposed to be in there. Okay, I was just trying to get you to smile because I knew at this point you'd be sleeping. Right, Darren? No, it's not mine. I just found that online. So this is a good example of local linearity here. Notice the viewing window. It's a really small viewing window, right? So on each axis, we're going from negative 1/10 to positive 1/10. All right? It looks like a line, doesn't it? Say yes. I think it looks like a line. In fact, this thing's pretty cool. It draws straight lines for me. So, oops. There's a straight line on top of what's there. Did you see what happened? Okay, it's a straight line in this viewing window. Okay, at least as far as we can tell it is. But if we zoom out on that exact same function, the red box is the viewing window we just looked at. It still kind of looks like a line, but it looks like we might have been a little sleepy or something when we drew that line. So now if I draw a line on top of this, you can see there's a little bit of curve to it, right? So I zoom out a little bit, and we lose a little bit of the line. And if I zoom out a little bit further, it turns into a function that we recognize. That is the blue one, is the sine function. Okay, that red line on there is a really good approximation for the sine curve if we're close to 0. Okay, if you notice here, there's not much of a difference between this line and the blue curve up until we get about to 1/2 here, and that's when it starts to split away. This could be really useful for us if we want to know what the value of sine is for something like 0.1. If you want to know what the sine of 0.1 is, it's going to be really close to whatever the value of this line is at 0.1. Okay? There's obviously going to be some error there, but depending on your threshold for error, your need for accuracy, it might be good enough. Okay? So if we zoom in on the sine curve far enough, it doesn't look like a curve, it looks like a line, which tells us then that the sine curve is that big D word. Differentiable, exactly. So in this case, we were zooming in on the sine curve at 0, so that tells us that the sine curve is differentiable at 0. If I were to zoom in on the sine curve in any viewing window, let's say I zoomed in on it like wait for it, say right there, it would still look like a line if I zoomed in far enough. Okay, and that's the key here. Looking at another curve, actually we're going to stick with the sine curve. This is a sine curve, right? Alec asked a good question, I think it was yesterday, if you could take more than one derivative, and I talked about Taylor series. You guys remember that? And we're going to take derivatives over and over and over again. Here's why that's useful. Not only can we approximate curves with lines, but we can approximate any curve with a polynomial. So this is the sine curve. This also looks like the sine curve, but it's not. Okay, within this viewing window, it looks like it, but watch what happens when I zoom out a little bit. Does that look like the sine curve now? Okay, so from here, it has all the properties of the sine curve that we would expect. It goes through 0, 0. It has a maximum here at pi over 2 and 1, or at least really close to it. It's actually slightly off, but you can't tell looking at it. It has a period of 2 pi. You can see here that it has a 0 at pi, or just slightly bigger than 3. So it has all those properties of the sine curve. But again, if I zoom out, it actually turns out that this is a polynomial. And the function that we're looking at here is that polynomial right there. X minus x to the third over 3 factorial plus x to the fifth over 5 factorial. You guys remember what these factorials mean? Yeah. So what is 3 factorial? 3 times 2 times 1, right? Which would be 6. 9 factorial is not as easy to compute in your head because it's 9 times 8 times 7 times 6 times 5 times so on. You guys know all the numbers, right? So if I throw the sine curve on top of this, notice that for that first period, from negative pi to pi especially, they look exactly the same. Okay? And this doesn't have as much to do with differentiability, although it does. If a function is differentiable, then we can use a polynomial like this to approximate it. But it says more about how we can approximate something like a trig function with something that's a little bit easier to work with, because polynomials are easier to work with than trig functions are. And if I wanted to know, for example, what the sine of, say, 3 is, I could put 3 into this and compute it fairly easily, a lot more easily than trying to figure out what the sine of 3 is by trying to draw triangles accurately and stuff like that. Let's move on here. Here's a function, and actually this is an example of what I was referring to with Alyssa here. This is the function y equals x to the 2/3. So I'll write that on here in case you're curious, because I know some of you are, maybe not all of you. This is x to the 2/3, or the cube root of x squared. That looks like this, and you guys notice here that we have a cusp here, right? Yeah? Okay. If I zoom in on it, I want you to note the viewing window right now. We're going from x values from -5 to 5, or I'm sorry, -5/10 to 5/10. If I zoom in on it here, where we're going from -5/100 to 5/100, there's still that corner there, right? And no matter how far I zoom in, I don't know if I have another one. Nope. No matter how far I zoom in, it's still going to have that corner there. Okay, does that make sense? So that means that this one right here, this function would not be differentiable at that point. So even though it's continuous there, it's not differentiable because it has that corner. Another example would be the absolute value function. If you zoom in on the absolute value function more and more, it actually doesn't change its shape. It still has that corner there. And the reason the absolute value function doesn't work, and I should have had this on here because this is a good example that's kind of easy to see. The reason the absolute value function doesn't work is if we think about what it means to be differentiable, that means we can find the what? We can find the derivative at that point, right? So there's the absolute value function. I'm going to slide it over just a little bit because I'm kind of a perfectionist. Okay, so there's the absolute value function. It doesn't matter how much I zoom in on it. This is going to be the function y equals absolute value of x in pretty much any viewing window. Doesn't matter how far I zoom in, it's still going to look like that. So this could be like -1/1,000,000th, and it's still going to look exactly the same. And +1,000,000th here. Okay, it still looks just like this. So the idea of differentiability is, are we able to take the derivative at that point? And the derivative tells us what? What does it tell us about the function at this point? The slope, right? Well, as we approach from the left, if we're coming from over here, what is the slope? -1. As we approach from the right, what's the slope? +1. Question?
So if we take the derivative coming from each side, and then two derivatives of it?
Exactly, yes. So what we can do here, and actually, let's go ahead and write this down. The derivative of this function, let's use different notation here. The derivative of our function y with respect to x is actually going to be a piecewise function. So if x is less than 0, the slope is -1. If x is greater than 0, the slope is +1. Where we run into trouble is when x equals 0. Okay? We can't just pick one and say, I like -1 better than +1, so that's going to be the slope. Or I like +1 better than -1. There's nothing here that says that -1 or +1 is going to be the slope. Now, I really like this example because some calculators use a symmetric difference quotient to compute the derivative. And if you use a symmetric difference quotient, what that means is instead of picking 2 points, so having a starting point here and then finding the slope of a secant line here and then moving this point closer to 0, what a symmetric difference quotient does is it picks one to the left and one to the right and finds the secant line, and then both of them move closer to 0. And by doing a symmetric difference quotient, your calculator thinks that the slope of the tangent here is going to be 0. But it's not, because it's not going to be tangent to it. It doesn't look like a line. It doesn't look like the line y equals 0. Some calculators do it and some calculators don't. So quick activity. Just looking at this graph here, and I just told you I'm being misleading, so you may know what's going to happen here, but just looking at this graph, it looks like this is not going to be differentiable at x equals 0, right? This function right here is the function x squared plus 1/10,000th to the 1/4 power plus 0.9. Okay? If I zoom in enough on this function, and you can do it on your calculator if you want, you certainly don't have to, but if I zoom in on it enough, it actually looks like what? Looks like a line, doesn't it? So what's happening here, and we can't see it in this viewing window, but this function actually looks more like this at that point. So it looks like a cusp, but if you zoom in enough, and you have to zoom in a lot, but if you zoom in enough, it actually does turn into a line rather than a cusp. So be careful. Again, don't trust what something looks like necessarily, but use what you know in calculus, and we're going to learn how to take the derivative of a function like this shortly. But trust what you know in calculus first, and understand your calculator, and your calculator is going to be misleading. Whether it tells you that the derivative of the absolute value function at 0 is 0 rather than undefined, or gives you a picture of something that looks like it has a cusp in it, but it doesn't, you need to be smarter than the calculator. And that's kind of the gist of this graph right here. Any questions about differentiability?